Welcome to the video on digital transmission and encoding techniques. This session covers signal conversion and the methods used to transform data for communication. Digital transmission involves the binary transfer of data using discrete signals. It forms the foundation of modern computer networks, ensuring high reliability and efficient long-distance communication. Digital transmission is favored for its benefits, including better noise immunity and high reliability. It also simplifies error handling and facilitates secure communication through encryption. Key components of data communication are the sender and receiver, which are the source and target devices. The medium is the physical path, and the protocol is the set of rules governing the exchange. We now transition to digital conversion, which includes line coding, block coding, and scrambling techniques used to prepare digital data for transmission over a digital channel. Line coding is the process of converting binary bits into digital signals. It maps data bits to voltage levels and is critical for receiver synchronization and determining transmission efficiency. The main goals of line coding are achieving synchronization between the sender and receiver clocks, reducing errors caused by noise, and eliminating the DC component to protect hardware. Line coding techniques are broadly categorized into three types: unipolar, which uses only one voltage level; polar, which uses both positive and negative voltages; and bipolar, which uses three voltage levels. Unipolar encoding is the simplest form, using a single voltage polarity. Typically, a positive voltage represents bit 1, and 0 voltage represents bit 0. Advantages of unipolar encoding include a simple design requiring minimal circuitry for implementation. This makes it an easy and low-cost solution for very short-distance applications. However, unipolar encoding has disadvantages, such as poor synchronization in long strings of identical bits. It also has a high DC component, leading to power loss and a limited transmission distance. Next, we explore polar encoding, which utilizes multiple voltage levels for enhanced performance in digital transmission systems. Polar encoding includes several techniques: non-return to zero, or NRZ, which uses simple voltage shifts; return to zero, or RZ, with mid-bit voltage changes; Manchester, known for strong synchronization; and differential Manchester. NRZ-L is a level-based signaling where the voltage level determines the bit value, with high voltage often representing binary 0 and low representing binary 1. There is no return to zero mid-bit. NRZ-L offers simple hardware detection logic and efficient bandwidth usage compared to RZ techniques, making it a common choice for its balance of simplicity and performance. NRZ-L faces challenges like baseline wandering, where it's hard to distinguish signals from noise over time. It also suffers from sync loss when long sequences of identical bits cause clock drift. NRZ-I, or inversion encoding, uses transitions to define bit values. A transition at the start of a bit interval represents binary 1, and no transition signifies binary 0. NRZ-I offers better synchronization than NRZ-L, as transitions provide more timing information. It also improves reliability by being less susceptible to total signal loss during continuous ones. Return to zero, or RZ, solves synchronization problems by returning to zero voltage halfway through every bit interval. However, this method requires 3 voltage levels and demands higher bandwidth. Manchester encoding is the standard for legacy Ethernet, combining NRZ-L and RZ. A transition always occurs in the middle of the bit, and the direction of the transition determines the bit value. Manchester offers benefits like being self-clocking, with a transition in every bit for perfect clock recovery. It also features zero DC, balancing signals to prevent DC component buildup. The main trade-off for Manchester encoding is a 2x bandwidth requirement. Due to the high transition rate, it needs double the bandwidth of NRZ to transmit the same amount of data. Differential Manchester uses mid-bit transitions for clocking, while transitions at the start of the bit convey data. A transition at the start represents a 0, and no transition means a 1. Differential Manchester boasts high robustness against electromagnetic noise and excellent synchronization, maintaining timing even in complex signal paths. We now move to bipolar encoding, which uses 3 distinct voltage levels: positive, negative, and 0, for data representation. Alternate mark inversion, or AMI, is a bipolar scheme. Zeros are represented by neutral 0 volts, while ones alternate in polarity between positive and negative voltage levels. AMI advantages include no DC component, as alternating voltages cancel out the average DC level. It also allows for simple error checking. Successive pulses of the same polarity indicate a line error. A major disadvantage of AMI is the challenge with zero sequences. Long strings of zeros leave the line at 0 volts, leading to a loss of synchronization. Therefore, AMI is often paired with scrambling techniques. Block coding is a technique used in digital transmission for adding redundancy. It enhances reliability by allowing for the detection of errors during transmission. The main purpose of block coding is error detection, where unused patterns signal a transmission error. It also ensures data integrity, helping the receiver interpret correct bit sequences. 4B/5B coding maps 4-bit data blocks to 5-bit code blocks. This technique ensures at least one transition per block, which helps eliminate long sequences of zeros and maintains synchronization. The benefits of 4B/5B coding include robust clock synchronization by guaranteeing enough transitions for the receiver clock. It also improves overall signal quality and resilience at the physical layer. Scrambling is a high-speed synchronization solution used in digital transmission. It modifies the data stream to prevent long sequences of identical pulses. Scrambling replaces long strings of zero voltage with special patterns. It maintains clock synchronization without increasing bandwidth, unlike Manchester encoding, and prevents quiet lines from being misinterpreted as disconnected. B8ZS, or 8-0 substitution, is a scrambling technique used in North America. It replaces 8 consecutive zeros with a specific pattern containing intentional bipolar violations to signal the receiver. HDB3, or high-density bipolar 3, is used in Europe and Asia. It replaces 4 consecutive zeros with a pattern based on the count of non-zero pulses since the last substitution. Next, we transition to analog to digital conversion, the essential process of converting real-world continuous signals into discrete digital data. The analog to digital converter process has 3 main steps: sampling, which measures the signal at intervals; quantization, which assigns discrete values; and encoding, which converts those values into binary strings. Signal sampling involves taking snapshots of the analog signal voltage at a constant rate. The quality of the final digital result is heavily dependent on the chosen sampling frequency. The Nyquist Theorem states that the sampling frequency must be at least twice the highest frequency component of the original signal to accurately reproduce it. Quantization maps continuous analog values to the nearest available discrete level. Quantization error is the difference between the actual analog value and the quantized digital value. Binary encoding first assigns each quantization level a unique integer ID. These IDs are then converted into n-bit binary sequences for digital transmission. Pulse code modulation, or PCM, is the standard for digital audio and telephony. It is the primary method for converting analog signals into digital form. The PCM workflow consists of 3 main components: the sampler, which measures the signal; the quantizer, which assigns discrete values; and the encoder, which converts the values to binary data. PCM is widely used across various applications. It forms the backbone of modern telephony systems, is the encoding standard for CD audio, and is used extensively in digital television broadcasts.